Let us revisit the example that we have done in the class, that is a water jet which impinges a flat plate, and the flat plate is connected to a cart, and the cart is moving with a velocity vc towards the right. The jet of water exits like this and it hits the cart. The jet velocity is given as Vj, and it is given that the jet splits into half, meaning at this point and this point the area of the jet is a by 2. Right. So the question is, what is the force required to keep the plate moving at a constant velocity? That is the main question. Let us look at the first approach, that we consider the control volume as this entity, and the control volume is moving with the cart. So the control volume moves with the velocity of the cart, that is Vc, and we are not fixed to the lab frame of reference, that is we are moving in a reference frame which also moves with a velocity Vc. So in that case, if we were to redraw the control volume, we have a jet which now comes in with a velocity of Vj minus Vc, and the jet exits after hitting the plate at a velocity which is yet unknown, but all we know is that the area through which the exit is made is through a by 2, where a is the area of the jet coming in. So from the conservation of mass, we have integral rho u minus b dot n dA is equal to 0. So in the frame of reference which moves with the velocity Vc, the velocity of the control volume is actually 0, because we are also in a frame of reference which moves with the same velocity as the control volume. So in this case, the influx will be minus rho Vj minus Vc times A, and the exit will be the exit velocity V exit times A over 2, and there are two such surfaces through the exit happens, so we will have a factor of 2 and this will be equal to 0. We have neglected the time derivative because it's a steady state problem. So in this case, we obtain that the V exit is equal to Vj minus Vc, and this is a very straightforward result. So now let us look at the linear momentum equation. So once again, it's a steady state problem, so we have integral rho u minus b dot n dA. This is going to be equal to summation of all the forces acting on the control volume. So now the control volume has to be acted upon by some force. Let us call it Fx and Fy, and we will neglect the weight of the cart, the weight of the plate, and the weight of the water inside the control volume. So we will neglect all masses inside the control volume. So we can now write down the x momentum equation from equation 1, and that will be integral rho u minus b dot n dA, and that will be equal to Fx. In this control volume and in the frame of reference in which we are moving with the velocity of the cart, the first term, that is the inlet, will be rho Vj minus Vc times, so because this b will be 0 in this frame, so it will be simply Vj minus Vc times the area, but there will be a minus sign. The other two fluxes in the frame of reference moving with the cart will have no x component of velocity. That is, in the frame of reference moving with the cart, the exit velocities are orthogonal to the plate. This is the plate, and the exit velocities are orthogonal to the plate. They have no component in the frame of reference moving with the cart. And so this will be equal to Fx, and this gives us the force, which is minus rho A Vj minus Vc squared. Alright. it is quite trivial to show that the Fy will be equal to 0 due to symmetry. In fact, we can directly see that whatever flux is exiting the top, momentum will be in the y direction. It's a positive momentum, this is the negative momentum because of the directions, and they will cancel out. The incoming flux of momentum has no y component, and therefore everything balances out, so there will be no Fy. Let us now look at the same problem in a frame of reference which is fixed to the lab. So once again we have the plate which is connected to the cart, and there is a jet of water which hits it like this. In this case, the cart is moving with a velocity equal to Vc, and the jet is coming in with a velocity of Vj. Right. So now once again the control volume will be this. The control volume is now moving with the velocity of Vc. This implies that the B vector is equal to Vci. But we are in the lab frame of reference. So in the lab frame of reference, let us now write down all the equations. So before doing that, the water which exits at this point will have a velocity which is the same as the velocity of the cart at this point. Therefore, the momentum at the exit as seen from the lab frame of reference will have a component of velocity equal to Vc, because when the jet strikes the plate, water cannot enter into the plate by no penetration boundary condition, and thus the water must possess the same velocity at the exit in the x direction as that of the cart. So over here the exit momentum will be Vc. Similarly, over here the exit is in this direction, but the water velocity as seen from the lab frame of reference, because the cart itself is moving, the jet itself at this point is also moving, and we will have another velocity Vc. Let us now write down the conservation of mass. Once again, it will be integral rho u minus b dot n dA equal to 0. In this case, at the first surface, let us call them 1, 2 and 3. So we will have at surface 1 rho Vj minus Vc times A, but there will be a negative sign because the area vector points like this. At the other two surfaces, we will have only the y component of velocities contributing to the mass flux because they are orthogonal at those surfaces. So we will have V exit. So this is V exit as seen in the lab frame of reference, which is static. So V exit times A by 2 times rho. This will be equal to 0, but there are two such surfaces, so this will be multiplied by 2. So therefore, the V exit is equal to Vj minus Vc. Now, let us apply the conservation of momentum, which will be simply rho u. So I'm just writing down the x momentum equation. U minus b dot n dA is equal to fx. So at surface 1 we will have rho Vj minus Vc times A with a negative sign because the normal vector at the surface points in the opposite direction of the velocity coming in. Now at surfaces 2 and 3, so for surface 2 we will have rho Vc times V exit times A over 2. This is the contribution of this particular integral at surface 2, plus at surface 3 we will have rho Vc times V exit times A over 2, and this will be equal to fx. So left hand side is minus rho Vj minus Vc times A, and the right hand side is rho Vc V exit times A, and the right hand side is simply fx. But we have already seen that V exit is equal to Vj minus Vc. So we have minus rho Vj minus Vc times A plus rho Vj minus Vc times A, and this is equal to fx, which implies that fx is simply minus rho Vj minus Vc squared times A, which is the exact same result that we had obtained earlier. So the two approaches do yield the same answer. The difference between approach 1 and approach 2 is only the Galilean translation of the frame of reference, which is the change of frame with a constant velocity. The physics of the problem, that is the final force acting on the plate, should not depend on the frame of reference that is chosen. It should be independent of that, and that we have established. In one case, we had the frame of reference moving with the cart, and in one case, we have the frame of reference which is fixed in the lap frame of reference. And the two approaches do yield the same answer. Do look at the video once again in case of any doubt. Thanks.